Welcome students to the fourth lecture of mathematical reasoning. In the last few lectures, we have understood the theory behind the mathematical reasoning, what is a statement, what is a simple statement, what is a compound statement and the roles of different connectors, etc. Today, I will be dealing with a few problems, so that you understand the concept of mathematical reasoning in a better way. So, first I look at negation. Find the negation of the following statements and verify their truth values. The function f x is equal to mod x is differentiable for all x belonging to R. We all know that this is not true, as mod x is not differentiable at x is equal to 0. Therefore, the above statement is false. Therefore, question comes, what is going to be its negation? The negation should be true. That means that the function mod x is not differentiable for all x belonging to R. So, this is the negation. So, we understand that even if it is differentiable at all other points, but just because of one point, namely x is equal to 0, the whole statement becomes false. Consider now the second problem. There is a perfect number which is odd. I hope all of you know what a perfect number is, but still let me just give you a brief introduction. A number is said to be perfect if it is the sum of all its factors excepting itself. For example, 6. The factors of 6 are 1, 2, 3, excepting 6 itself, and their sum is 6, which is the number that have been given to us. Similarly, 28, its factors are 1, 2, 4, 7, 14, and their sum is 14 plus 7 21, 21 plus 4 25, 25 plus 2 27, plus 1 is equal to 28. Now, as of today, we did not find any odd number which is perfect. So, we can assume that this statement, there is a perfect number which is odd, is false, because so far we have not got any number which is perfect, but odd. Therefore, what is going to be its negation? Its negation is going to be all perfect numbers are even, because there is a perfect number which is odd, its negation, there is no perfect number which is odd, that means all perfect numbers are even. So, original is false, therefore, the negation of it is going to be true. Now, let us look at another problem. All triangles are either isosceles or equilateral. We know that this is false, because there is another type of triangle which is called equilateral triangle. There are triangles which are equilateral. Therefore, what is going to be the negation of that one? All triangles are either isosceles or equilateral. Therefore, its negation is what it is? Not all triangles are isosceles or equilateral. I made a mistake here, which are scalene. This is false, because there are scalene triangles also. So, the negation is, it is not true that all triangles are either isosceles or equilateral, and this is going to be false, because this is going to be true, because there are scalene triangles. So, what is true? What is true is all triangles are not isosceles or equilateral. Now, let us see another problem. If A is a quadrilateral and A has all sides equal, then A is a square. Is it correct? No, this is false, because rhombus is a quadrilateral that has all four sides equal. Therefore, what is the negation? The negation is, it is not that if A is a quadrilateral and A has all sides equal, then A is a square. This is true. This is true because of the existence of rhombus. So, this is going to be true. That is the beauty of negation. If something is a false statement, then its negation is going to be true, and if something is true, then its negation is going to be false. Before I move to the next set of problems, let me make a small digression. In this respect, let me talk about quantifiers. If you have noticed, then the four problems that we have solved, we have seen that either the original statement is something about all and its negation is talking about one exception, so that the above statement is truth value is reversed. So, if something is claimed to be true for everything, its negation will try to show that there is an exception. If something is said to be true for one, then its negation will show that it is false for everybody. That brings us to the concepts of quantifiers. So, what is a quantifier? I am coming to that, but before that, let us understand what will happen to statements like this if we want to negate them. There are triangles that are equilateral. Is it true or false? It is true. Let us look at this statement, some rectangles are squares. Is it true? It is true. Some rectangles are squares. See, a lot of students love maths. It is true? Yes. Then what is going to be its negation? So, let us look at how do we interpret the negations of these sentences. There are triangles that are equilateral. It is true. Then, if we write negation of A as there are triangles that are not equilateral, then we find that this is also true, because of course, there are triangles that are not equilateral. So, on one hand, we are talking about a statement, there are triangles that are equilateral, which is true. Then if I interpret its negation as there are triangles that are not equilateral, then that is also going to be true. Similarly, statement B was some rectangles are squares, which is true. If I write its negation as some rectangles are not squares. That is also true, because there are rectangles which are not squares. So, statement B, which was some rectangles are squares, which was true, we found that its negation, some rectangles are not squares, that is also true. A lot of students love maths, that is true, but if I write negation of C as a lot of students do not love maths, then that is also true. So, we are getting statements which are true, and we are also finding that the negation of those statements are also true. That should not happen, because we know that the negation of a true statement is false, the negation of a false statement is true. So, why it is happening? The apparent fallacy is due to the presence of quantifiers such as some, a lot of, several, etc. Because if something is true for some objects, then it is not true for some other objects, right. So, the negation also turns out to be true. Therefore, in the mathematical reasoning, the type of statement that we deal with they are clearly true or false for the entire set of objects. So, if something is true for every object, or for all objects, then its negation, then it will be proved to be false if there exists at least one element for which the above statement is false. So, the above discussion tells us that essentially we look at two types of quantifiers. one is called for all, typically we symbolize this like this, and 2 there exists. Which you symbolically write like this. As we have just seen that if something is true for only a subset of things, then it is not mathematically defined what is going to be its negation. So, the type of mathematical reasoning that we are working on for this course, which is sentential or proposition based, reasoning, works with only with the above two quantifiers. There are logics of higher order where we can deal with other quantifiers, but that is not within the purview of this course. Now, let us look at the following problem. Consider the following statements: P, A is a triangle, Q, all sides of A are equal, R, A is isosceles. Which of the following expression denotes the negation of A is a triangle with sides of different lengths implies A is isosceles, right? So, if you remember, P is A is a triangle, Q, all sides of A are equal, and R, A is isosceles. We need to find the negation of A is a triangle with sides of different lengths implies A is isosceles. We want the negation of that one. As you can see, this is a compound statement, where the components have been given. A is a triangle, therefore, P is true. So, we can write P, which is true, with sides of different lengths. So, Q, all sides of A are equal, but we want all sides of the sides of different lengths. That means that we are looking at that Q is false, that is, we are looking at not of Q, and we want to see that this implies that if A is isosceles, that is, if P and not Q, then R is true. So, the above statements, the above compound statement, when we break it into its components and symbolically represent, then this compound statement becomes P and not Q implies R. So, the question that has been asked is, what is the negation of that one? That means, what is the negation of this. Okay? And we have been given 4 alternatives. We have to find out which of these following is the correct alternative for this. Now, let us look at the alternatives. So, these are the alternatives, and we need to find out negation of P and not Q implies R. How to do it? Is it not of P and Q implies R? Is it P and Q implies not R? Or is it P and not Q or not R, or P and not Q and not R? Okay? So, we have to see. So, we have to simplify this expression. We have seen in the last class the following. A implies B can be written as not A or B. If you are not convinced, let me show it using the truth table. Suppose A and B. A can take values t, corresponding to that B can take values t or false, true or false. Similarly, we can have A and B as false and true, and A and B can be false and false. If you remember, then we know that A implies B. Therefore, we will have the truth values as following: true implies true is true, true implies false is false, false implies true is true, false implies false is also true. Now, let us look at what is not A. Not A is going to be the opposite of A. So, when A is true, not A is false. When A is true, here also it is false. Here A is false, therefore, not A is going to be true, and here it is false, therefore, it is going to be true. And B had these values T, F, T, F. Therefore, not A or B has the following truth values: false and true is true, false or true is true, false or false is false, true or true is true, true or false is true again, because we know that under OR the compound statement will be true if any one of them or both are true. So, here not A is false, but B is true, here both of them are true, here not A is true and B is false. Therefore, in all these 3 cases, not A or B is equal to true, but only in this case it is false. Now, let us look at what is the truth value of A implies B. It is true, and not A or B is also true, false, this is also false, here it is true, here also it is true, and here it is true, here it is true. Therefore, we observe that A implies B and not A or B are equivalent. Therefore, negation of A implies B is same as negation of not A or B, and this we can write as we have done in the last class, the De Morgan's rule. It is not of not A, which is A, and not B, right. Therefore, negation of A implies B, we can write it as A and not B. The statement that we are looking at is P and not Q implies R, and we want its negation. We have negation of A implies B is equivalent to A and not B. Therefore, we apply the same here. We have negation of A implies B. Therefore, we can write it as P and not Q, which we can call it as A, and R, which we call it as B. Therefore, negation of P and not Q implies R will be P and not Q and not R. P and not Q and not R. Now, the four options that were given to us are not P and Q implies R, P and Q implies not R, P and not Q or not R, P and not Q and not R. So, this one is coming out to be the right one for us if we compare with this, that P and not Q and not R, provided and is associative. So, we want to show that and is associative. So, we take P, Q, R, three statements, and the way we were doing for two statements, the four possibilities of truth values, true, 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 false, false, true, false, false. Now, we have 3, therefore, we will have 2 to the power 3, that is 8 possible values. Let me write them in a systematic way. True, true, true. Keeping P and Q same, I can change the truth value of R. Now, let me change the value of Q to F. Here also we can get two possibilities for R. One is true and the other is going to be false. Now, we take the next combination for P and Q. We have exhausted all values, all the possibilities with P is equal to true. Now, we write F T T F T F. Now, F F T and F F F. These are the 8 possibilities that the 3 statements, the truth values of the 3 statements P, Q and R can take. Now, we want to find out what is P and Q and R. P and Q can be true and true, which is true, and R, which is true. So, this is T. P and Q again true and true, but R is false. So, P and Q is true and R is false. Therefore, this is going to be false. P and Q is true and F, therefore, that is false. Therefore, if this is true, still we get false. True and false, which is going to be false again, and false. Therefore, this is false. Now, we can see P and Q is F T, which is false, and T for R, that is also false. F and T, which is false and false, that is also false. It does not take much time to understand that these two are false again. Now, let us look at what is going to be the truth values for P and Q and R. So, P is true, Q and R is T and T, this is true, therefore, this is going to be true. P is true, Q and R are T and F, so that is F. Therefore, the whole expression is T and F, which is going to be F. Similarly, T and F and T, which is F, is equal to F. T and F and F, which is F, is equal to F. F and T, which is equal to true, that but they are combined and is F. Similarly, F and T and F is F is equal to F. F and F and T, which is F, is F, and F and F and F is F. F and F is F, therefore, the whole thing is F. So, if we look at the two columns, we can see that the truth values of P and Q and R and P and Q and R are same, or in other words these are associative. Therefore, in the last example that we have done, we were looking at P and not Q and not R. Because of the associativity, this is correct. Now, there are three other alternatives. I want you to work with these alternatives and try to find out what do they mean. I leave it as an exercise for you. Okay? Let me move to the next problem. Which of the following are tautologies? What is a tautology? A statement which is always true is called a tautology. This we have discussed in the last class. Now, our job is to see which of the four compound statements are tautologies. So, what we will have to do? All are involving only two variables, two statements P and Q. So, we have to find out the truth value of these statements and against all possible arrangements of truth values for P and Q, and then we will see if that gives us true, then this is true or this is a tautology. Similarly, we will have to do for all of them. So, this type of questions can be of multiple choice, and one can ask you how many of them are tautologies, and the possible answers can be 1 or 2 or 3 or 4, or one can put it in different combinations and ask you to put the right one. So, in today's class, I will take up all the statements one after another, and then I will try to see whether they are tautologies or not. Okay? So, first statement, P and P implies Q implies Q. As before, I take the four possible choices of values for P Q, namely true true, true false, false true and false false. We will now see if P and P implies Q, what is its truth value, then we will have to see what is the truth value of that implies Q, and then we will see whether that is true or not all the time. So, let us first look at P implies Q. Since I have done it many times, I just want you to recollect that true implies true is true, true implies false is false, false implies true is true, false implies false is also true. So, P implies Q has the truth value corresponding to the different combinations of values for P and Q. Therefore, what is P and P implies Q? So, I am ANDing the truth value of P with the truth value of P implies Q. Therefore, P and P implies Q, it is T and T is equal to T. P and P implies Q is true and false, which is false. Here it is false and true, which is false again. Here it is false and true, which is false again. Now, we have to look at what is the truth value for P and P implies Q implies Q. So, this is what we have got, P and P implies Q. Now, we will look at what is the truth value of this implies Q, where Q is given here. So, truth implies truth is true, false implies false is true, false implies true is true, false implies false is true. This we know from our knowledge of the truth values for P implies Q, and here we find that for all the possible cases, these are all true. What does it suggest? It suggests that P and P implies Q is a tautology. Let me look at the second problem. What is the second problem? To show that or to check that if not Q and P implies Q implies not P, whether this is a tautology or not. So, as before, we will start like this. We have P, Q, we have the same combinations T T, T F, F T and F F. As before, we have for P implies Q, we have T, F, T, T. Therefore, when we AND, okay, before that let me write not Q. Not Q is opposite of Q. So, since Q is true, it is false, it is false, it is true, it is true, it is false, it is false, it is true. So, not Q and P implies Q is going to be AND of these two columns, which is false, false, false and true. Now, we want to check if this whole thing implies P, not P, what will happen. So, not P has the truth value opposite of P, which is false, false, true, true. Therefore, our job is to see what is the truth value of this implies this. And we find that this is false implies false is true, false implies false is true, false implies true is true, true implies true is true. Therefore, we can see that not Q and P implies Q, the whole thing implies not P, is a tautology. Problem C was P or not Q or not P or Q. As before, I will do it rather quickly. P Q, we have T T, T F, F T, F F. So, P or not Q, P or not Q. So, with respect to Q, we will take the opposite value of it. So, T and not Q is false. So, true or false is true, true or negation of q is true. So, that is also true, false or negation of q is false. So, OR of 2 false is false, false and negation of q here is true. So, OR is true. So, P or not q is T T F T. On the other hand, not P or q is not P or q. Negative of P is false, false or true is true, false or false is false, true or true is true, true or false is true. Now, I am looking at the OR of these two. So, it is true and true and the OR is true, true or false and the OR is true, false or true it is true, true or true it is true. Okay. So, here also I find this is a tautology. Therefore, P or not Q or not P or Q is tautology. The last expression, that was D, which was P implies Q implies P or P implies Q implies Q. As before, P implies Q is going to be T F T T. This we have done many times. Therefore, P implies Q implies P. This is going to be true implies true is true, false implies true is true, true implies false is false, true implies false is false. Now, what is P implies Q implies Q? P implies Q, T implies T is T, false implies false is T, truth implies truth is true, true implies false is false, right. Therefore, if I look at all of these, I find T, T, T and F. Therefore, this is not true in all the possible interpretations of P and Q. Therefore, this is not a tautology. Therefore, the answer to the question which of the following are tautologies, we can see that A, B, C are tautologies. Okay, students, I stop here. I will take one more class on mathematical reasoning, where I will be solving a few more problems and I will give you some concepts which will be useful for solving some of these problems.